GTC enthusiasts, please welcome to the stage Google Chief Scientist Jeff Dean and NVIDIA Chief Scientist Bill Daly.
So Jeff, it's been an exciting year for machine learning. What's sort of most exciting development you've seen the past year in machine learning?
Yeah,
what do you expect to see next year also?
Yeah, I think everyone in this field has seen, really rapid progress in what these models can do and what the capabilities are, and also how people are applying them. So that's been really interesting and exciting. I think for the last year or so, I would say reflect on a couple of different things. One is, I feel like the models have gotten way, way better at sort of problems with verifiable rewards, so things like math and coding. 3 or 4 years ago, we were super excited when our models could, solve 8th grade math problems. Fred has 4 rabbits and gets 2 more rabbits, and then they would get that, 40 or 50% of the time. Everyone was like, yeah, that's great. But in the last few years, and particularly in the last year, we've really accelerated how effectively these models can do mathematics. And so you saw like our Gemini model entered the IMO contest and got a gold medal. In coding contests, the ICPC contest, we also got a gold medal there. So I think the capabilities in those domains are really impressive. And then maybe a little bit even more recently than that, we've started to see really agent-based workflows work extremely well for longer running kinds of things. It used to be you could ask your model to do some stuff and it would go off and do it, and a few minutes later you'd have to now say, okay, great, it finished that, and what's the next thing it can do? But now you can actually give these models tasks that take hours or perhaps even days, and they will go off and independently kind of do a bunch of things, correct themselves, do some more things. And I think that's a pretty exciting transition, because now it leads to the ability to have these models kind of operate fairly autonomously for longer periods. And that, I think, is a very different thing, whereas before you'd kind of have to sit there, not quite interactively, but supervising them fairly closely. So that seems like a pretty exciting change. Speaking of this, it seems like we're going to have a lot more of these agents kind of operating in the background, and that one of the things that's really going to be important is how do we get ultra-low latency inference so that these systems can, do their work autonomously, faster, because I think that's a really rapid driver of how effectively they can solve problems. How do you see the next architectures you at NVIDIA are working on delivering, major latency reductions? How do we think about getting to, instead of hundreds of tokens per second, to thousands or tens of thousands?
Yeah, I talked about this in my talk at 10 o'clock this morning, which I think was recorded if you missed it. And there are a bunch of answers to that question. When you look at the sort of performance curve for inference, it's a trade-off between, at one extreme, if you're willing to give up latency, you can get very high throughput in sort of tokens per second per dollar or tokens per second per watt. And then you can move down that curve, and basically running smaller batch sizes, you can optimize more for interactivity, more single user tokens per second at the expense of that throughput. As you get down to the right side of that curve, where you're really optimizing for latency, it turns out that the bulk of the delay is communication latency. And so we're working on developing architectures where we drive that latency down to what NVIDIA we always refer to as speed of light. And if you look at a typical LLM where you're doing a bunch of feed forward stages, then a bunch of attention stages, and that's one layer, and you do that for anywhere between 50 and a couple hundred layers. Every time you finish one of those stages, there's usually an on-chip communication to get to the next stage. And then after you finish a layer, it's often an off-chip communication to get to the next layer. And sometimes even between stages within a layer, depending on how you partition the problem. And on-chip, we've got trial designs whereby statically scheduling things so that there's no routing overhead, there's no queuing, there's no arbitration. We basically can achieve 2 millimeters per nanosecond, basically the time of flight over wires on the chip, and get from one corner of the chip to another corner of the chip in 30 nanoseconds. That really drives the latency down from several hundred nanoseconds today. And then off chip, a lot of the latency is actually in our PHY, because for years we have optimized these PHYs for the maximum bandwidth without too much consideration for latency. And so to push the extremes, we wind up with heroic digital signal processing to pull this super noisy signal off the wire and run all sorts of fancy math to figure out what the bit is. And even then the bit's kind of noisy, so then we do heroic forward error correction to pull the right bit out. And it turns out if you back off on the bandwidth just a little bit, go from, say, 400 gigabits per second per pair to 200, all of a sudden, all that goes away. You can just detect what the voltage on the wire, you get the bit, and it's just serialization latency at that point. It's a couple clock cycles going on and off chip. So we see our way to build whole routers, similar to the routers I built at Cray 20 years ago in 2006 when we did the Black Widow. The router was less than 50 nanoseconds, pin to pin. I think we can do that again. And by doing that, I can see us running relatively big models at 10 to 20,000 tokens per second per user.
Yeah, I mean, that's super exciting. I think this is it's really important to be able to run the largest scale models at these scales, at these low latencies.
Yeah. So you talked about these agentic systems, getting to the point where you could give them a task and run off for a while. How closer do you think we are to the point where we can take one of these agentic systems and just have it do the next version of itself? Take whatever the current version of Gemini is, give it a long-running task, maybe a month, and it goes off. It basically experiments around, comes up with the right model, comes up with the right data curation strategy. Runs the data through there, decides how it's going to acquire more data, maybe writes a couple contracts to do that, and trains the next version of itself.
Yeah, I mean, I think that the whole thing you described is not quite there yet, but I do think we were starting to see signs of that emerging as you can ask the model at a very high level, please explore ideas in this rough space for improving the performance of the model. And it'll go off and run, 50 experiments. It'll dismiss, 40 of them. It'll hone in on 10 that seem promising, do follow-up experiments. I think one way I've been characterizing this kind of work is, for a while, there's been meta-learning. In, for example, 2017, some people in the Google Brain team did some work on neural architecture search, where you can sort of specify a search space of potential architectures, then run lots of experiments at small scale to find the architectures that seem to learn the best on a particular set of problems you care about. And we've done that with learned optimizers and learned activation functions and so on. And so in those cases, 8 or 9 years ago now, people were specifying those search spaces as code. But I think one of the really nice things that we now have is the ability to specify interesting research spaces in natural language. Right? It's like, please go make yourself better. Please
models,
explore interesting new distillation algorithms and try to use information we're not currently using, and it will go off and do those experiments. And I think that's a powerful
natural language NAS.
It's basically a super powerful multiplier for researcher productivity, because all of a sudden you can, it's really easy to think researchy thoughts. It's actually harder to run the experiments and get the results and sort of interpret them. And if the agent can do a lot of that work, that's really going to be a great sort of partnership between super capable researchers and super capable agents. So let's see. One of the challenges that always exists when you're building hardware, especially in a fast-moving field like machine learning, is if you start a new hardware project today, it might pop out the other end and actually be in data centers in 2 years if you're sort of lucky. We'd like that to be shorter, but then it has to live for a certain number of years. And so you're really trying to predict where is the machine learning field and AI fields headed in the 2 to 5 year time window. And that's always been a super hard thing to predict well. And I'm wondering if you've come up with good tools or mechanisms to help do this kind of crystal ball reading effectively.
Yeah. So we try our best, and part of the way we do that is by trying to develop our own models, both LLMs like Nematron and world models like Cosmos, our robotic foundation models like Groot. But as hard as we try to do that, and we're trying to kind of look out ahead, developing a model that's not yet the one that people have, we get surprised. There's lots of people out there working on this. They're super clever. They're coming up with great ideas every day. And so we kind of have to future-proof our hardware. And we do that in a number of ways. First, there are things you do that are just good for all models, right? If we can come up with a way of doing math more efficiently, perhaps due to better number representations, that makes everything better. Similarly, if we can sort of organize our on-chip communication to just reduce data movement, that makes everything better. Where we tend to run into places that we really wish we knew what was coming down the pike are when people change the model in a way that changes the provisioning, sort of how much math you have versus how much memory bandwidth versus how much memory capacity versus how much communication, because those are the things that even if you make each of those 4 ingredients really efficient, you got to decide how much of each to have. And then when somebody comes up with a different model, like going from group query attention to multi-head latent attention, it changes some of those ratios pretty significantly. And all of a sudden, you're leaving some pieces of hardware idle and others busy. And there's really no way around that, except perhaps in the future, if we see a bunch of different models needing different sorts of provisioning, the volumes are large enough, we may just do different SKUs provisioned in different ways and kind of hedge our bets against that kind of the future.
Yeah, makes sense.
I guess it's my turn. Not yet. Okay, so historically, at least in recent history, we tend to scale our models according to the chinchilla scaling laws. And if we had a certain amount of compute, from that we would decide, we would have so many parameters and usually about 20 times that number of tokens. But now we've gotten into this realm where it's really hard to get more tokens, but we'd still like to continue scaling our models, use more compute to do the training. What do you see sort of filling that gap? With data mined out, how can we use more compute to get more accurate models?
Yeah, I think first I'll clarify, chinchilla scaling laws are optimal for training, right? If you start to consider inference performance of the trained model, then it may be that you don't necessarily want to follow exactly that. I also kind of disagree with the assertion that we're running out of data. I feel like there's an awful lot of data in the world that is not yet being used to train these models.
Where do you see this data?
Well, we train on some video data, but I think there's a lot more video data and with associated audio data that that we aren't necessarily training on yet. I think real-world kind of robotics or autonomous vehicle data is going to be fairly plentiful. And synthetic data is another recourse for how do you generate really interesting, high-quality data of you just inject more compute, you can get synthetically more data for training your models.
Don't you wind up sort of regurgitating the same stuff after a while? If you trained on some data and then use that to generate synthetic data, it's sort of another version of the same stuff.
Yeah, but it still seems to help the model sometimes, because if your model is very powerful, the one that's generating the synthetic data, then it actually does seem to help quite a bit. Yeah. So I think that's where, and then there's all kinds of techniques we're not yet using that were in vogue for, say, image models, convolutional image models years ago. So I think things like
data augmentation.
Of which you can think synthetic data is a little bit of that. Techniques to prevent overfitting are interesting. You can use dropout or distillation as ways of regularizing the model. So I think there's a lot of opportunity there to really make models better with more compute and more passes over the data where you won't overfit necessarily.
Yeah. So. Do you ever see the LLMs getting to the point where we train them the way we trained AlphaGo, just to have the LLMs kind of conversing with each other and somehow improving their performance by doing that?
Yeah, I do think the current pre-training regime is sort of like you take your model, you throw your random number generator at it to initialize it, you strap it to a board, and then you stream all the internet data past it. And it learns what it can from that observation, but it's not actually taking actions in the world. And it seems like we want to interleave some of that with something where the model gets to take actions in some environment, be it simulated robotics environments or trying to predict answers to questions or things like that, and then going back to learning, and maybe where it's also a bit more directed in how it chooses what data to see next, as opposed to a predetermined kind of ordering of the data. And I think that would actually be quite interesting as a way to dramatically improve essentially the learning efficiency, right? For a given number of tokens, how much can the model get out of it? And I feel like taking actions in the world is going to be super useful for that. And we do that in post-training, but that's a very limited form of that. I think interleaving this kind of thing much more.
Interleaving it at the pre-training stage.
At pre-training stage. I mean, we sort of have this artificial distinction now, and it doesn't seem like that should exist for the long term.
I guess it has to get smart enough where sort of that makes sense. So when you start out with a random number generator, it probably can't do that. But after you've thrown some number of tokens
show it 10 billion tokens, and it can probably do something. Yeah. So scaling of training workloads has been a really big focus for the whole sort of community for the last few years. But we're starting to see, as these models have much more influence in the real world, that inference workloads are becoming, much more important. And traditionally we've sort of tried to build chips that are good at both of these things. And NVIDIA recently acquired Grok, which has like nice low latency inference hardware. And I saw you made some announcements combining the Grok hardware with your sort of latest generation GPUs. How do you think about the differences between hardware needed for training and hardware needed for inference?
So that's a really good question, and I'll go further. I think it's not just that inference is starting to become important. Inference is the job now. It's easily 90% of
I was underselling it.
Of the power in data centers is going into inference, and the good news is there's a lot of similarities between both. And it's interesting that, for example, number formats like NVFP4 that we developed originally for inference have proven to be remarkably effective at doing training as well. But it's still a very different task in terms of what the demands are, particularly in terms of the memory system, because with training you've got to keep all the activations around for the backprop step, and in inference you just kind of throw them away as soon as you're done with them. So there's a larger need for memory capacity. It drives, like what I said before, a different amount of provisioning between memory capacity, memory bandwidth, math, and communication. But we see that same difference in need for provisioning even in different stages of inference. So for example, the prefill stage is a lot like training in that you get all these tokens you can operate on in parallel. So it tends to be very, very math heavy and dominated by communication energy if you're not careful about localizing your data. And then you get to the decode stage of inference, and you now are doing these, especially if you're latency optimized, you're doing matrix vector or matrix, very skinny matrix products, and you're extremely memory bandwidth limited and latency limited. And then even that is broken into kind of the feed forward and the attention stages that do different things. And so I think that it's a natural division over time to build different components provisioned for these different stages. And I suspect you'll see at least 3 flavors: one that's good at training and prefill, one that's good at and one that's good at decode, and that one that's good at decode may even bifurcate into the attention decode and the feed forward decode.
Yeah, it makes sense. I do agree that like prefill looks more like training than the decode stage, which looks quite different.
Yeah, well, the decode stage is just so sequential. You got one token, you got to run it through everything.
Yeah, I mean, I think one thing that helps is like speculative decoding. Can give you like instead of a vector, you get a slightly skinny matrix.
Instead of 1, you get 8.
Right?
And diffusion LLMs can do even better, possibly doing blocks up to a few hundred.
Yep.
Yeah. Oh, that's I got to somehow queue up the next one in my head while I'm answering yours. Where are my darn questions here? Okay. Okay. Yeah. So I'm going to skip that one.
We're skipping questions. That's why this is challenging.
Yes. So new models are appearing on a regular basis with new forms of attention, diffusion transformers, hybrid state space transformer models. What do you see on the horizon for models? What excites you most in the model zoo at present?
Particularly in attention, you think?
Across the board. What?
Yeah. Well, I think clearly we've been moving more towards larger parameter count sparser models. So that has a huge impact on what does the memory footprint of these models look like? How do you activate the right pieces of them?
Right.
And
So
typically,
MOEs, yeah.
MOEs, you're typically activating a tiny fraction of the overall parameter count. And when you have a batch of things, typically you're activating different ones of those, which is a bit annoying. And then I think
sort of destroys some of that batching because now they're going different
it does.
places.
Like you had a huge batch, and now you made it a tiny batch. And then I think in the attention space, there's a lot of interesting potential improvements to the naive quadratic attention. The quadratic attention algorithm works extremely well for quality, but it's extremely expensive once you start getting to large token counts. So you do need to do something to scale beyond, say, 1 million tokens or something. And I think there's a bunch of possibilities that have been sort of proven out at modest scales and look quite promising. So one is I'll categorize them as things that reduce the constant factor of the quadratic attention substantially. So you can pay attention to chunks of tokens and then identify which chunks seem most interesting and then delve into those chunks only and not the full thing.
Right, but that's not just constant factor. That's changing it from n squared to some n log n or something, or n to a
well, no, it's still n squared because the chunks might be 128 in length, and you're still doing quadratic attention to those things.
Okay, I see what you're saying, but what you do for each thing can be much smaller. So
so that helps. And then there's some interesting things where you can, for example, cluster the attention state, and then only look at the clusters that are near the thing you're trying to do. And those actually can be sort of n log n, or perhaps even better in terms of.
Perhaps,
And so that seems quite promising as well. I mean, I think the trade-off there is generally you lose a little bit of quality relative to the full quadratic attention. So it's a question of is that useful? And then I think there's also a notion of the models are very good when you put the right information in the context window because they can pay attention to it. But the attention window is not big enough to be what you would really want, which is I would like to attend to all information, right? Like all the documents on the internet, or for me personally, all my email and photos and so on. And that's much bigger than 1 million tokens. So I think the right sort of way to give you the illusion of attending to, say, 1 trillion tokens instead of 1 million is to have staged forms of much lighter weight retrieval mechanisms that then sort of identify what are the
because you don't need all trillion at once for a particular task. You'd like to somehow select.
What are the 10,000 documents
which
that are
million
most
of those trillion you really need? Pull them in and then attend to that.
And maybe that's staged. You don't go from 1 trillion to 1 million. You go from 1 trillion to 10,000 documents of 10 million, that's maybe 10 or 20 million tokens, and then you look at them with a much lighter weight mechanism to identify what are the million-ish total tokens I'm going to put in. So I think I'm pretty excited about that because I think that kind
of a hierarchical attention mechanism.
That approach kind of will enable you to do things that just the sort of attention window size won't permit. So I'm a big believer in the use of AI for various aspects of chip design. Both, if you think about the chip design phases, there's like high-level architectural explorations, there's more automated synthesis of high-level designs into lower-level things, there's automating verification, and then there's automating placement and layout and routing. And so I've done some work on Alpha Chip as one example, helping with placement and routing.
Very great Nature paper, by the way.
Oh, thank you. And that's been really useful for a bunch of generations of TPUs that we've designed. And how do you think? And I've seen some really nice work from NVIDIA on various kinds of gradient-based methods for placement and routing. So how do you think about the use of AI in the actual hardware design process? Do you think tackling these different stages with different AI-based approaches is the right thing? Do you think a much more end-to-end thing is possible? How do you see this evolving?
So we're trying to use AI wherever we can in our design process, and there are a number of examples. So for example, every time we have a new semiconductor process, we have to port our standard cell library to it. It's about 2,500, 3,000 cells, and that used to take a team of 8 people about 10 months, so 80-person months. And then we developed a program based on reinforcement learning called NVCell. I think we're up to NVCell 2 or 3 now, and it's overnight on one GPU. And the results are actually better than the human designs. In measures of goodness of size of the cells, power dissipation, delay, it matches or exceeds the human designs. So it's a huge productivity gain, and it eliminates an obstacle to moving to new processes, because now we can move cell libraries over very quickly. And then we have this program called Prefix RL, which applies reinforcement learning to a really age-old problem in computer design, which is where to put the look-ahead stages in a carry look-ahead chain. And this is a problem that's been studied since the 1950s. And this RL program goes at it like it was an Atari video game, and it puts something in here and it grades itself. And it's not trying to make the fastest adder; it's trying to make actually the adder that barely meets timing and is as small and low power as possible. And it comes up with totally bizarre designs that no human would ever come up with, but they're actually 20 or 30% better than the human designs by those metrics. And then at a more holistic stage, we've for a number of years have had a series of LLMs that we've called ChipNeMo and BugNeMo. And what we did is we took a generic LLM, and then we fine-tuned it by feeding it all of the design documents proprietary to NVIDIA. So this is stuff that you can't get outside the company. It's all of the RTL.
Hardware design docs.
Yeah, all of the RTL for every GPU ever designed at NVIDIA.
Yep.
All of the architecture specs for those, all sorts of stuff. And now you have this LLM that's actually very smart about GPU design. And one of the biggest gains of this is when you have a junior designer, it turns out the senior designers spend an enormous amount of their time explaining to the junior designers simple things like, how does a texture unit work? And particularly this texture unit. And now they don't have to ask the senior designers that. They can ask ChipNeMo that, and ChipNeMo will explain to them in great detail how the texture unit works. They have a follow-up question that will answer the follow-up question. So it improves productivity that way.
It's a very patient mentor.
Yeah. and the same thing when we have bugs, we can have it summarize bug reports and try to do attribution on bugs. Say, which module is this bug in? Who do we arb? We always arb somebody for a bug, action required by. And so we'll decide what designer gets arbed for a particular bug. And then we're at the more exploration level, and particularly in NVIDIA research, we're now using agentic systems to try to do a bunch of thought experiments where we say, okay, here's a bunch of different ways we could go, figure out what this parameter space looks like, suggest new ways of doing things, run simple architecture experiments, and whittle the design space down to a smaller number of things that we can look at. And we're trying to collapse the time. At NVIDIA, there's a stage when we're kind of done with the exploration effort that we have the F model. It's basically an executable model of the GPU to where we tape out the design. We have all the geometry done. It goes out to TSMC to make chips. And we'd like to collapse that space. And it turns out what the real long pole in that space is design verification. And so we're particularly looking at how we can use AI to prove that designs work more quickly. There are also a couple stages in there where we have to refactor the design, because we have, the RTL design is done, but then we've repartitioned things for floor planning, and now we have to move parts of the logic from one module to another and make sure everything still works. And those are the kind of things that I think we ought to be able to automate, and we should be able to collapse that time period down. But all that said, I'd love to have the end-to-end stage where I could simply say, design me the new GPU, and I'll go out skiing for a couple days, and I'll come back, and it's done. But I think we're a long way from that. But I think it is making us much more productive.
Yeah, I think making every stage of that automated process fast enough that it can actually explore this enormous design space is super challenging.
And I think even when we get to the end-to-end, it's going to be sort of the master agent calling on these agents who are specialized in the different parts of that pipeline to carry out their parts, and then perhaps to iterate when it's not happy with the quality of the result.
Yeah, and potentially even split up in the same way we split up human chip design teams, where you have this agent focusing on this part of the chip, and then this one over here with some well-known interfaces between them, and then they have to negotiate changes to those
exactly.
interfaces.
They'll have the same kind of meetings we have, but between agents.
Yes. Interagency meetings.
Okay, I keep forgetting I have to ask a question now. I should have organized this in 2 columns or something. Okay, let's see what we got here. Yeah. So on that topic of agents, if you have teams of virtual engineers and swarms of agents collaborating on complex projects, what are the biggest orchestration and continual learning challenges that hardware innovations could dramatically accelerate? Things like hierarchical rewards, sparse activations, dynamic model growth. What do you see happening there?
Yeah, I mean, I think one of the big challenges in ML these days is how do you get systems working where the reward signal is sparse and maybe not as verifiable as, say, math or coding, right? If you can really crack that, then I think you can learn to do a whole bunch of different tasks from dramatically expanding out the set of capabilities of the areas of expertise of these models. I do think there's some challenging things because as we get these agent-based systems, they typically look like they have a whole bunch of trajectories that they're rolling out. You'd like those to be as low latency as possible in the model to generate, the next bit of code or the next set of actions the model's going to take. And then they're going to interact with some environment. And often the way they interact with that environment is they use tools that were designed for human speed interaction, right? And so even...
And often run on CPUs.
And run on CPUs. And so, the startup time of your C compiler is not necessarily something that people pay, they pay some attention to, but they need to pay a lot more attention to it in this world where you have an agent that is operating, 50 times faster than a human. And the startup time of all your tools, I think, is going to start to be a Amdahl's law-like bottleneck, because if you make your model infinitely fast, you're going to get, depending on what you're doing, a factor of 2 or 3 end reduction in latency if your tools are a pretty significant fraction of what you're doing. So I think we're going to need to start to really re-engineer a lot of the tools that these models...
So do you see this happening right now for coding tools?
Yeah, it's happening for coding tools. It's happening for, even being able to sort of manipulate your spreadsheets and your documents. The tools that can extract that information programmatically, are not necessarily the things that are super speedy at doing that. And I think we'll need sort of new forms of tools. Let me see. So energy is something I've seen you talk about in a bunch of your talks and slides. And the thing that really sticks with me is what we ultimately are trying to do is like a multiply add operation or something, which is a fraction or a few picojoules depending on the precision. And then in order to actually make that happen, we have to bring that data from some part of the memory system, and that's a factor of 1,000 more in many cases, more energy. And given the fact that we're really pushing and trying to make these systems as energy efficient as possible, I'm curious what you think are going to be the big improvements. I mean, you spoke to some of these of shrinking the distance that things have to go across the chip. That can help, but maybe you have a more broadly characterized set of techniques.
So to put the numbers straight, typically doing a multiply add, say for NVFP4, is like 10 femtojoules.
Yeah.
And to pull those 4.5 bits in, from HBM4 at order of maybe 3 or 4 picojoules per bit, you're talking about 15 picojoules. So it's 1,000 times more energy to read one NVFP4 number from memory than it is from external memory than it is to do a multiply add. But reading a simple SRAM bank is also on the order of about 10 femtojoules.
Yeah.
And so the key thing you can do to reduce energy is to just don't move data. And no, people are laughing, but I'm serious.
No, that's how you do it.
That's absolutely what you have to do. And so, for example, we're looking at designs where, for where we can put things in SRAM. We have an SRAM. We can read a row of a matrix out of that SRAM, have a row of a activation vector, and do a dot product right there. And so we've done 2 things. We've done basically say 1,000 multiply adds. with no data movement. We just read the SRAM, everything is there in place. We do 1,000
Read from your left hand, read from your right hand.
That's right. Yeah, and then we've reduced the data from being 1,000 long to 1 by doing the dot product. And so we're trying to look at a lot of techniques like that. And then the problem then is that SRAM is expensive in terms of area per bit. It's an order of magnitude more expensive than DRAM. And the technology we're really excited about, but it's not quite ready, is where we can stack the DRAM on top of the chip that's doing the computation, and then we can basically cycle the DRAM mat, as they call it, and sense the bit and bring it straight down. And it turns out most of the read energy of reading the DRAM isn't actually reading the DRAM, it's moving the bit from where you read the DRAM over to where the pins to the GPU are. And so by putting this DRAM directly on top of the GPU, we can get an order of magnitude more bandwidth with an order of magnitude less energy per bit, which winds up being the same power, but with way more performance. And those are really the things we're looking at doing. Of course, more efficient models will help also. I mean, if you can get the same accuracy with less work, that reduces energy also. Yeah. And the one place there that I think that can really help a lot is with sparsity. We've already done a lot with sparsity, starting with Ampere with the 2-to-1 structured sparsity, but these models are just very naturally sparse. But it's also the case that other than the 2-to-1 structured sparsity and the very coarse sparsity of MOE, it's hard to exploit sparsity in a way that wins, because once you start exploiting it in a more general sense, you create a lot of irregularity, or I should say you destroy the regularity, and the regularity is a lot of what makes a computation efficient, because you get all the bits kind of marching along in regular order. When you disrupt that, you now need to do much more control-oriented and data routing-oriented things to deal with an irregular nature. So I think it's really kind of an interesting open question, how to push to the next level on sparsity.
Yeah, definitely. I mean, I think models that kind of reuse their parameters for many times are kind of nice in some ways.
Yeah, reuse is good, but reuse is again, it's part of that curve trading off, optimum throughput, optimum tokens per watt against optimum interactivity. And when you're really worried about interactivity, or when you're only running a single model, and you have one token, it's got to see every weight. The reuse is 1.
Yeah, unless it's like a convolutional model, in which case you get quite a bit of reuse.
You get the spread of the convolution. But for LLMs, it's a your matrix vector. Okay, that's right. It's my turn. So somebody needs to flash a little light. Bill, your turn. Okay. So your TPU co-design loop, where you sort of predict ML research directions 2 to 6 years ahead, bake them into silicon, has been remarkably successful over I forget what generation you're on now. What are the top hardware-software friction points you're seeing at Google today, especially in the mixed GPU, TPU, or multi-cloud environments, that the broader industry should be solving?
Yeah, I mean, I think, yes, we definitely do quite a lot of co-design, because I think you really do want to get your hardware designers and your ML researchers talking to each other and into the same room fairly often, so that they can bounce ideas off each other, because often what happens is an ML researcher will say, I think we're going to be doing a lot of this in a year or 2 or 3. And the hardware people kind of look at that and they'll be like, oh, that's interesting. And then they'll be like, oh, well, we can't quite make that really fast. What if we could make this thing that's, not quite that? Would that work for you? And that kind of interaction. And the ML researchers then sort of say, oh, well, maybe we could prototype this. And
they sort of realize what is possible and what is easy and what is hard.
Yeah, and I think that kind of interaction is really, really important. I think we sort of, because we design the hardware and we do a lot of modeling and ML research, we do have a nice window into where we think the field might go. And one of the things we sometimes can do is put a little bit of, experimental things that we think will be useful 2 to 4 years from now into the silicon. And we, obviously hopefully bet correctly, but if we don't, it's not like a huge disaster, because then that just means that little bit of the chip will be underused or only used in certain circumstances. But if it actually does work, then it pays off big, and you can
Right.
suddenly accelerate something like 10, 20x in the hardware.
It's kind of like our CUDA tax and all of our GPUs used for graphics. Yeah, you just put a little bit in there, and if you can use it, it's great. If not, it's not a big deal.
Yeah. So one of the things that is a big trend right now is having much more continual learning systems. And one possibility for how those might evolve is instead of like a fixed model with a set of parameters, you have some more organically growing model architectures that sort of add parameters or maybe prune parameters away or compress existing sets of parameters into smaller sets so that you free up some memory for other things. What hardware features do you think would be helpful for that? Or are there features that won't tank utilization if we have these like really weirdly organic model structures?
Yeah, I think it's a real question of what the granularity of that irregularity is. As long as you have a big enough block that you can kind of, schedule something very efficiently to run, and then you can dynamically select what is the next block. It might be bigger, it might be smaller. Then I think you can still do it very efficiently because we can apply all the techniques we know today to make those individual blocks run efficiently. And then the really critical thing is, in any parallel computing system, is synchronization and communication. And we've been working very hard. I think we have lightning fast synchronization mechanisms these days. So when one block is done, you can detect it's done and fire the next one off, and then it will be a little bit of a question in that your communication will probably be less choreographed than it is in a very regular computation. But again, if we can apply the principles that give us speed of light, latency and minimum energy, we should be able to communicate from the output of one block to the input of the next block very effectively. So I think we can do a pretty good job of handling dynamic computations.
Yeah, I kind of agree. As long as things are a minimum size.
That's right. As long as you don't try to push it down to one op.
Yeah, then it'll be
like maybe 10,000 ops.
Yeah, 10,000 ops is good. Yeah. Otherwise, we're back to a CPU.
Yeah. Okay. We're running out of questions, so we're going to have to open it up to the audience.
I know.
Yeah. And we didn't think we'd get through these questions. We should have made more. Okay.
It's true.
So to hit the 10,000 plus tokens per second regime for reasoning heavy agent workloads, which algorithmic techniques, advanced speculative decoding, MOE routing at massive scale, ultra low precision inference, do you think will require the biggest corresponding hardware changes, like deeper support for per vector quantization, optimal clipping, or logarithmic representations?
Yeah, I think to really make low latency inference effective for very large models, you have to think from first principles about what can we do to minimize the data movement, minimize the energy, and minimize the time to go from an input to the output of a block or a layer or attention calculation or whatever. And those things really are probably about rethinking how that entire hardware pipeline looks, not about like a particular, numeric format here or there. I think it really requires kind of rethinking quite a lot about the inference hardware, because really you don't want anything to move. Someone laughed when we said that earlier, but I think that's really the key is don't move anything, and it'll be super efficient and super low energy.
And you can do that if you put everything in SRAM, but then it becomes super expensive.
Yeah. So, new memory technologies are always welcome, I would say. I think the stackable DRAM on top of a chip is probably a pretty interesting direction, because then you can get much more capacity and cheaper cost per bit and still have you don't move the data very much. It's like a pachinko machine where you just drop the bit you want down into the operation. So I think those are probably really exciting directions, is how do you make incredibly large models, very low latency? Because that, I think, will improve the whole use of agents and all the, assuming we make our tools fast enough as well, that will really dramatically, improve the energy usage of these systems.
Yeah, on the numeric, front, what NVIDIA were down to NVFP4, and a lot of people are copying that or doing similar sort of block scaling formats. Do you see any more really exciting, again, to get these energies down, developments in data representation? What are the things on the horizon there?
Yeah, I mean, I think having something where you have a representation that is very few bits, and then you have scaling factors that are applied to chunks, many of those units, is probably a pretty effective way of dealing with the very low precision that you might have in each individual thing, but then enabling you to sort of pretend like they're all much higher precision. And that seems like a very effective technique, and we've been doing quite a bit of that as well.
Yeah. Have you looked into things like using lookup tables? You can put each symbol exactly where you want it, but you only get a few of them.
Yeah, I mean, that's definitely something we've been thinking about a little bit, because I think it does mean your computation logic becomes a little more complicated, but it can be worth it sometimes. So maybe we can, I'll ask you something not in our doc.
Uh-oh, I'm unprepared.
So one of the things about our TPU designs is they have custom networks that tend to be 2D or 3D toruses, sort of kind of point-to-point things. But they scale to very large numbers of chips, thousands of chips. And that is a different approach than, say, a sort of fully switchable network fabric that enables you to scale to larger than just a machine worth of chips. How do you think about the trade-offs in these two designs? And
well, that's a great question. You realize that one of my major academic research areas was interconnection networks.
I know.
And I literally wrote the book on this subject. And it turns out that 2 and 3D torus networks are really great for a lot of things. In fact, I kind of led a revolution in the late 1980s, early 90s to have a whole series of supercomputers designed with almost all 3D torus networks. The Cray T3D being the sort of the big example. And then into the 2000s, what happened is we got so much pin bandwidth on chips that when you're building a router chip, you couldn't really effectively use it if you only had 6 connections, which is what you get with a three-dimensional bidirectional network. And so we moved into this area where we built what we called high-radix routers, and we moved to a whole series of new topologies like folded clo networks, which are often called fat trees, and dragonfly networks and things like that. And it really you can't say one is better than the other, because it really has to do with what is the workload and what is the traffic pattern. If you have a very local workload, a direct connected network with relatively low radix like a 3D torus is really ideal, because you can map your problem. So part of the problem is on this TPU, and part of the problem is on this TPU, and you have to go one hop to get your data over there. But then there are other cases where, for example, you have an MOE model, and you've got a lot of experts, and they're scattered all over the place, and now you're having to take many hops to get to a given expert. And so it would be more efficient to do one hop up to a switch and one hop down to the expert that you really want to be at. When we've played around with some of these trade-offs, we've often come up with a hybrid one. We had one, sort of experimental inference system that will never see the light of day that we did in NV research, where the local communication to allow things right next to each other to communicate was a direct connection, no switches, but with a flattened butterfly topology. So you had a little bit more reach than you have with a torus. And then all of those chips were also connected to a switch, and all the more global communication was done through a hierarchy of switches.
Yeah, I mean, I totally agree. It depends on exactly what your workload is.
That's right. Given a traffic pattern, you can come up with an optimum network.
Yes.
But there's no network that is good for all traffic patterns.
Yes, indeed, indeed.
Oh, that's right. I got to come up with one now, and I've used all of mine. So I have to think of something clever. So as we build these wonderful machines that run wonderful models that do things that become even more amazing every day, what do you think is going to be the most positive impact on sort of human existence out of this? Is it in education or medicine or business productivity? What are you most excited about the fruits of our labors improving for humankind?
Yeah, I mean, I think this is a really good question. I think there's obviously a whole range of things that AI can be applied to. And some are incredibly societally beneficial, education, healthcare. Some are, potentially things we maybe don't want a lot of use of. And I think I and a bunch of co-authors got together about a year ago and looked at a whole bunch of different areas. So it's my only paper with its own website, shapingai.com.
Shaming AI, wow.
Yeah, but we looked at 7 different domains that would be potentially heavily affected by AI. And education was one of them, healthcare was one, labor and employment was another, science was one. I think the ability to accelerate scientific discovery is a potentially really interesting one. Media and both generation of media with video generation models and image generation models, but also misinformation as a potential, potentially negative consequence. Those were some of the areas, and I'm particularly excited about healthcare and education because I think if you think about education, we know that when people have an individualized tutor who knows what they know, knows what the material is the person is trying to learn, and knows how that person learns best, that is much more effective than a sort of more group education setting. Educational outcomes, I think, are 1 to 2 standard deviations higher when you have a personalized tutor than when you have a more group setting.
Right. Now everybody can have a personalized AI tutor.
So if everyone can have a personalized tutor that knows how they learn best, and I think one of the cool things about these models these days is they can actually turn one modality into another, so that really helps people who learn best by maybe listening to a podcast about the biology chapter rather than reading it sequentially, or that want to play an interactive game to explore gravity rather than read the equations in the physics textbook because they get more intuition and feel for it. And I think that's sort of within reach in the next few years, is to have these amazing educational tutors that don't give the answer away, but help people learn the concepts better and more efficiently and more effectively.
Yeah. It's interesting because in a lot of the schools these days, people are trying to restrict the use of AI, where instead they ought to be encouraging students to learn how to work effectively with AI.
Yeah.
And the tutor's almost even orthogonal to that. It's
yeah, I mean, if you think back to when calculators were first introduced into math classes, there were some math teachers who said, "Oh no, we can't use calculators. People will never know how to add or multiply." But instead, it just meant that we could teach mathematics where the calculation wasn't the bottleneck.
Right.
And instead,
So you could I think move up to a higher level much more quickly.
I think educators should really be leaning into the fact that these tools exist and will do interesting things. I mean, maybe I can turn it around to you and say, what are the application areas of AI that excite you the most, and where you think will have the most impact?
Well, the 2 that excite me is, first of all, AI for hardware design. Since I'm fundamentally a hardware designer, I'm interested in, basically, being able to get my job done in about 15 minutes. I go out and do something fun for the rest of the day. And I think that we talked about this. There's a lot of really productive stuff there. And a lot of it is just keeping track of all the documentation with the project and being able to query information you need quickly and summarize bug reports and stuff like that. But I think we're also getting very close there to being able to ask it to design a texture unit. If you've explained to it enough what a texture unit is, it can probably come up with a pretty good design. What's harder though is to say, take the texture unit that we have in the Blackwell generation, and here are the new things that it has to do for the Rubin generation. Here are the features we've deprecated. Make the minimum change to move the code from one tree to the other one. But then the other one for me is also education. I'm a recovering educator. I was a professor for 26 years, and I think it really is. I'm hoping somebody is doing this. Maybe I should quit my day job and go do it myself. And having a personalized tutor. Another thing which is of a similar vein is to have a personalized health coach, right? So it's a little, think of this as a little angel sitting on your shoulder. And I went to Jensen's panel today. When I got to the lounge, all the food was gone, but they had all the dessert there, right? And so my lunch was dessert. But if I'd had my little health coach on my shoulder, it would have talked me out of that.
Or it would have deserted you.
I think that a lot of the nation's health problems are are basically issues with diet and exercise, and if we all had personal health coaches, I think just like being able to reach a student, understand what motivates them, they could interact with us, and we have this shared goal of not dying, and they would encourage us along that path.
This is the health setting, not the education setting, right?
Yeah.
Calculus class is not that bad. Yeah, I mean, I'm particularly excited about health as well. I feel like, first, there's so much information that is not used in healthcare settings that is relevant to people's health. Like I wear a heart rate monitoring watch, but does my clinician use that information?
No. And we could easily sequence everybody, right? And then have very personalized healthcare based on what mutations you have that may indicate your susceptibility to particular disease as a response to certain drugs, and a lot of that is even known that it's being completely ignored by most healthcare providers.
Yeah, and your little health coach, I think, is a really good idea, because I think the healthcare system.
And one thing they could do is talk to the doctor and say, well, did you consider the fact that Professor Daly has this mutation and that drug may not work well?
I see you're at McDonald's the 4th time this week. Did you know there's a great salad place around the corner or whatever? So I mean, I think that the use of AI for healthcare, I think, is going to be really impactful. It's a complicated environment because of very real privacy and regulatory issues, but I think we should aspirationally try to get to the world's past healthcare decisions being used to inform future healthcare decisions. And if we, as close as we can get to that, would be amazing. All right, I will ask you a more philosophical question. So NVIDIA has been incredibly successful in the last decade. How do you think, you've probably hired a lot more people, the company is a lot bigger, you have a bigger footprint in the world. What has changed that you miss, and what is used to work well and now no longer works at a larger scale?
Yeah. So it's interesting. So I started consulting for NVIDIA in 2003 when I was still on the faculty at Stanford, we're definitely right around 1,000, maybe a little bit less than that at that point. And everybody kind of knew. You didn't know everybody, but you knew sort of everybody you needed to know, and decisions just happened very quickly. There was zero bureaucracy, and there's a lot of things I miss about those days because there is now bureaucracy. You grow to be a 40,000 plus. We're still a relatively small company in terms of number of people. 40,000 plus person company. All of a sudden there are lots of rules, and there's various bureaucrats that sort of get in the way of doing the right thing at the speed of light. But I think that's needed because as you grow, there's sort of at a small size, people do the right thing because it's like part of a community, and you would never, want to do something that your fellow community members would be displeased with you about it. But as the company grows and you sort of lose that sense of community a little bit, that's when you start needing the rules. And I guess probably the thing I miss the most is losing a little bit of that sense of community. But what's amazing is Jensen has been able to create an environment where even at 40,000 people, it's still to first order feels like a startup, and I really like that. And then the thing you get is that there are things that are possible now because of the size and the scale and the resources available that we just couldn't do back then. And I think that we need to sort of take advantage of that, and make sure we chart our future using that capability to do the most good.
Yeah. I mean, I've had a similar experience joining Google when we were quite small. We were all wedged in above what's now a T-Mobile store in downtown Palo Alto, and now we're 180,000 people or something. And I feel like every doubling in company
that's like 4 NVIDIAs.
Every doubling in company size kind of caused something that used to work to no longer quite work as well, and you have to kind of figure out how to navigate that as a organization to instill just the right amount of new way of doing things, but without making things overly bureaucratic. So it's a challenge.
Yeah, well, I see Maggie standing in the wings there, so it must be about time for us to.
Thank you so much, everybody, for coming. It was a real pleasure. Jeff, awesome. Phil, awesome.
Thank you.
We're going to take a quick selfie with the crowd. If you could just Stand up.
Oh,
Okay,
Turn around.
turn
all right,
around.
here we go.
We're going to take a selfie with the crowd. Woo! 1, 2, 3. GTC! Thanks, everybody.
Thank you.
Well, thanks so much for doing this.
Thanks,
Jeff.
everyone.
This was a blast.
Yeah,
And
yeah.
I liked the back and forth with questions.